Okay, this is problem number 1 from 7.2. So let me bring up our my sketch pad here. All right, so remember we normally the probability of an event is equal to what? It's equal to the number of outcomes or ways for the event to occur divided by the total number of ways for anything to occur. Right, that's what we learned about in the last section. Now, the total number of ways for anything to occur, that's another name for that is the sample space, the size of the sample space. The sample space is the collection of all the outcomes, all the possible outcomes. So the size of that, the number of total, will be the number of total possible outcomes. Okay. The problem is we don't have a listing of all the days, and we don't have a listing of like what the weather was on all the days. That would be the sample space. The sample space here would be the listing of all the days of the year and then the different weather. We don't have it. Okay, so we have to rely on other properties of probabilities because in this particular problem, because we don't have a listing of all the outcomes. Okay, well, one of the basic laws of probability is called the complement rule. Okay, what's the complement rule? The complement rule says that the probability of an event the complement of an event is 1 minus the probability of the original event itself. Or vice versa, the probability of an event is 1 take away the probability of its complement. Complement means opposite. So the complement of rain, of a rainy weather, so if that's my event, so if my event E is rain, then the event, that tells me that the complement is the opposite. Okay, so then the complement of that event would be what? The complement of rain would be no rain. Okay? So if they want to know the probability that it will not rain, that means they want to know the probability of E complement. Okay? So the probability, there's a 75% chance that it will rain tomorrow. So that means the probability of the event E is 0.75. Because remember, 75% written in decimal form is 0.75. So we know the probability of the event E, which is rain, is 0.75. So what's the probability of E complement? We can just use our complement rule. Probability of E complement is 1 minus the probability of the event. Okay, so that means it's going to be, that means that it's going to be 1 minus 0.75. Okay, what's 1 minus 0.75? 0.25, right? Okay, easy peasy. 75% chance of rain, so 25% chance of not rain. And that's it. Okay, that should be at 0.25, make that a little clearer. Okay, that one should be pretty easy, all right? Complement is 100% minus the probability of the event, or if you're in decimals, 1 minus the probability of the event, okay? Typically, we do probabilities in decimal form. All right, so let's go to problem, I guess let's do problem 2. Okay, so here's our second problem, and let's just bring up the writing tablet. So the idea here is, can we just get the probability of 2 events occurring at the same time? That's what this is asking for. When you say A and B, that means they both are occurring at the same time. That means both events, that's an arrow, both events occur at the same time. What's the probability of that happening? Is it just the multiplication of the 2 probabilities? Well, let's think about a scenario. Okay, what if we had, let's say my 2 events were you wear sneakers or you have no sneakers. So you're wearing sneakers or you're wearing like dress shoes, whatever, some other kind of shoes. Let's say not sneakers. And let's say I've got a classroom full of students, and let's say most of them are wearing sneakers. I'll just kind of use a box, like let's say all the sneaker people are sitting here, and all the non-sneaker people are sitting here. Okay, so there's a lot more sneaker students, but that's okay. All right. Now, what if I also look at another characteristic of the students or another event, such as do you drink coffee or not? Now, a lot of students drink coffee, right? In fact, probably most do. So let's think of coffee like this. Let's say that about 75% of the sneaker people drink coffee. So about 3/4 of the kids who wear sneakers drink coffee. So this will be coffee, and this will be no coffee. Okay. And now what about the people who don't wear sneakers? Will that affect your coffee drinking? Is coffee and sneakers related? I don't think so, right? So if 75% of the people who wear sneakers also drink coffee, then roughly probably 75% of those who don't wear sneakers also drink coffee. So in other words, let's say the probability of sneakers is like, I don't know, 60%. Let's say this is like 80%. So probability of sneakers is 0.80. What about the probability of coffee by itself? That's going to be, let's say, 0.75. Okay, so roughly 80% of students 80% of students wear sneakers, 20% don't. Let's just as a guess. Okay, of the sneaker kids or students, 75% of them drink coffee, and 25% don't. Okay, those are what are called independent events. They don't influence each other. So we can just multiply them. We can say, for example, this box right here, probability that you wear sneakers and you drink coffee. Let's say sneakers and coffee, okay, is going to equal the probability of being in this row, probability of wearing sneakers, times the probability of drinking coffee. They are independent of each other. You can just say, well, 75% of everyone drinks coffee, so 75% of the sneaker people are going to drink coffee. Okay, so you're already 80% of students wear sneakers, and then we take 75% of them to see who also drinks coffee. So this is sneakers, and this is coffee. And so the probability of both happening at the same time is simply the multiplication of the two probabilities because they're independent. They don't really influence each other. But let's look at a different scenario. Let's look at sneakers again. Okay, so here's sneakers again. Sorry for the noise effect there. Okay, so here's sneakers. No sneakers. Okay, and now let's look at a t-shirt. Do you wear a t-shirt to class? Okay, so now let's say that overall most students wear t-shirts, but the thing is the students who wear sneakers are way more likely to wear a t-shirt than the people who don't wear sneakers. How come? Because if you don't wear sneakers, you're probably getting dressed up for some reason, so you're less likely to wear a t-shirt. So let's say the scenario is like this. This is of the sneaker people, these would be sneakers and t-shirt, and this would be no t-shirt. I'll say no T. Okay. What about if you're not wearing sneakers? It's probably, more like this. This is t-shirt, no t-shirt. Okay, you're splitting it here. In other words, if you don't wear sneakers, it's very unlikely that you're also going to wear a t-shirt. You're much more likely to not be wearing a t-shirt because you're probably dressed up. In other words, we cannot just multiply the probabilities because whether or not you wear sneakers is influencing if you wear a t-shirt or not. So here I cannot multiply, we can not multiply the probabilities to get the overall probability of both events. Why? Because they're not independent. They influence each other. Okay? So is this true? It's only true if they're independent events. Okay, if they're not saying that they're independent events, we cannot make the assumption that you can just multiply the probabilities. Okay, you can in a situation like sneakers and coffee. They don't influence each other. If 80% of students wear sneakers and 75% of students drink coffee, then 75% of the 80% would be students who both drink coffee and wear sneakers. 80% chance you're going to wear sneakers, 75% you're going to drink coffee, so 75% of the 80% would be coffee drinking sneaker wearers, okay? So that's kind of the idea. If they're independent. These guys are independent. These guys are not independent. If they're not independent, you can't multiply the probabilities, okay? Cool. All right, let's go on. Okay, so this is number 3, which is actually a really good example of the independence principle that we just talked about. So remember, I'm flipping a coin. Okay, so here's my coin. I'm going to flip it. So that's my coin. I'm going to flip it. I either get a heads or a tails on my first flip. Now I'm going to flip the coin again, and I either get a heads or a tails. I don't know which one, 50-50 chance. And I'm going to do this 5 times. Now, is the result of each flip, is it going to influence the next flip? So for instance, if I got a heads on this first flip, does that change the likelihood I'm going to get a heads on the next flip? And the answer is no. The coins are independent of each other. Okay, you can think of it as one coin being flipped 5 times, or just think of it as 5 separate coins, each one being flipped once. Okay, they don't communicate with each other. They don't talk to each other, right? I don't hear coins, whispering to each other. So they're not in the chances of getting a heads or a tails in one flip is not influenced by the previous one. Okay, so what's the chance of getting heads on this? So probability of the event heads on the first flip is obviously going to be 0.5. What about on the second flip? Probability of heads is also going to be 0.5. Now technically, we haven't. This is actually 7.2, so technically we haven't learned conditional probability yet, but a better way, a more accurate way of writing this would be probability that number 2 is a head. We got heads on the second flip, given that flip number 1 is heads. Technically, we're asking about a conditional probability, but we don't even need to think about that here because we can solve the problem without that consideration. The probability of heads on the first flip is 0.5. Probability of heads on the second flip is 0.5. Am I allowed to just multiply? So suppose I want to know what the probability is of getting both of the heads together, like that, heads and heads. So probability of getting heads on the first and heads on the second. What if I want to know what that is? And the answer is, can I just take the probability of heads on the first flip and multiply it by the probability of heads on the second flip? If they're independent, yes, which is what we just talked about. Are they independent? Do they talk to each other? Coins don't typically talk to each other, right? I mean, sometimes you get like a tricky coin that might want to talk to another coin, but that's not too frequent, right? Okay, so the answer is yes, they're independent. Okay, so I can just say that it's 0.5 times 0.5, okay, which of course is 0.25. Now that's the probability for the first 2. What about if I keep going? Okay, well, we're just going to keep multiplying. In other words, the probability of, what about the third heads, the third coin being heads, and the fourth one, and the fifth one? They're all independent of each other. Can I just keep multiplying? Yes. So it's going to be 0.5, the probability. Am I allowed to just keep multiplying? And the answer is yes, indeed. Okay, I can just keep multiplying because they're all independent of each other, which means you're allowed to multiply the individual probabilities. The probability of what's called the joint event, the event of all 5 coming out heads, is the same as each individual coin coming out heads, all multiplied together, because they're independent. Okay, that's where they're getting this number from. All right, so it's a good example of what we talked about before about independence. All right, so let's see. Let's go on to the next one.